Um, yeah, one second. Let me just replace. Okay, can you guys see it?
Yes.
Okay, perfect. Yeah, so I think this is going to be more of a discussion call in general because like the pure way that they did it, like the pure method, they didn't publish it yet. But I think it's cool to just look at what's out there and what is possible if you have a huge infrastructure in terms of GPUs and TPUs and yeah, what OpenAI is doing these days. Right. So Sergey already sort of showed this in his picture to announce this to announce this talk. So yeah, DALL-E is just a sort of a mix of DALL-E, Salvador Dali, the famous painter, and Wall-E. It's basically a smaller version of GPT-3, which may sound weird if you look at the amount of parameters it has, because it has 12 billion parameters. But to compare, GPT-3 has like 755, I think, 754. And it also builds on concepts such as image GPT. So I'll do a quick recap of GPT-3. So GPT-3 is a big NLP model. It has 175 billion parameters. It's autoregressive. That means it predicts the next word each time. And it's a few shot learner. So it can fine tune on new data sets with a few examples, and it doesn't need any gradient updates on those new data sets. And so a few examples of what GPT-3 can do is that it can learn to do arithmetic, although it's just a purely natural language model. And it can also learn to generate newspapers articles. And I just pasted one of the results here, which is for the, yes?
Can it do like really large random arithmetics rather than like 1 + 1, like something that it has?
No, I think it goes up to like 3 or 4 number
Oh, okay,
arithmetic.
so it is
I can look it up. It's not super big, yeah. It's not super, but it's just cool that it sort of learns to do arithmetic just by training a natural language processor. I think that was pretty cool. But so this is just an example of like the results they get. So this is the human accuracy of identifying whether it's written by a machine or by humans. And you can see that as it becomes bigger, the GPT-3 model, the human accuracy goes down and the confidence interval becomes smaller. So basically people can distinguish between a news article that is written by GPT-3 and by a human. And the reason why news articles is interesting is because it wasn't actually trained that much on news articles. So this is a few shot generalization it's doing because it says in the paper that when they show like the first few words of a news article, it actually thinks it's a tweet and it will finish as if it was a tweet. So they have to, fine tune it on news articles to do this. Right. Image GPT. So this is not based on GPT-3, but on the GPT-2 architecture. And the way it's doing it is it's basically going from picture to picture. So you get again, it's doing it autoregressively. So you get a few pictures in, and then it has to predict the next picture. And these are a few ways. So this is like the input picture it gets, and these are the ways it can finish the picture. So image GPT is from image to image. Yeah.
I saw somebody took those old first Mars pictures from Soviet whatever station that landed there and ran it through GPT, and it put an old Volkswagen rusting in the background.
That's pretty funny, actually. Right. So it can do image completion, and yeah, you can see that it has some pretty funny ways it can complete the images. Pretty realistic in a way. I guess most people in real life maybe wouldn't finish it like this, but it's still not too far off from something you can imagine happening. What it can also do is sample images. So these are some examples of sampled images from ImageGPT. But the main ideas to do completion. That's actually also how it's trained, because it's trained to predict the next pixel using autoaggressive modeling. It's also based on transformer, so both GPT-2, GPT-3, they're both transformer models. Right. Okay, so DALL-E, there's not a lot available about how they train it, but I thought I'd just go through the website. They have a lot of examples of what it can do, and I think that is the most interesting part actually, is because like Harsh said, we can't train this for ourselves anyways. So I mean, it's basically just a huge transformer model, and most of the implementations they actually new stuff they do is cool ways of implementing this model efficiently on like a TPU, because it's so big that that's the main sort of work you have to do, is like the implementation. Right. So DALL-E is also a transformer model because it's based on GPT-3. It receives both the text and the image together as a single stream of data. So the difference between, for example, image GPT and GPT-3 is GPT-3 is language to language, image GPT is image to image, and this is the next step, which is language to image. And the way it works is they so first they reprocess the images to 256 by 256. And then each image is then compressed to a 32 by 32 grid of a discrete latent codes. And that's done using a VAE. So basically, they do a sort of pre-trained pre-processing of the images, and you get a 8-bit 32 by 32 grid, which is sort of a very compressed representation of an image. And then what it does is you have what they call our tokens. And so, for example, you can imagine that each letter in our alphabet is a token. So we have 26 tokens in our alphabet. And what they do is they have image captions that are represented using tokens, 256 to be exact. And the way they produce these tokens is using byte pair encoding. So they kind of try to compress the image caption into a very efficient encoding. Byte pair encoding, I can pull this up because I feel like it's not super well known. One second. Right, so the way it works is that it says here, the most common pair of consecutive bytes is replaced with a byte that does not occur within the data. So basically, if you have AAA, BD, AAA, BC, then you can replace the byte pair AA because it occurs most often, and it will be replaced by a byte that's not used in the data. I mean, it's not super important how they do this exactly, but you can just imagine that this is like a way of compressing language into a little bit more efficient sort of, yeah, it's just a little bit more efficient.
One more question. This way. So we have this one-hot representations, then we came up with dense representations, word vectors and things like that. So where does this lie? I'm not, like, I don't know if I understand how each token is represented. Is it a vector, a number, or like?
So I think it's a 0 or 1. They don't go too much into what a token is exactly, but I think it's a 0 or 1. Because the reason why I'm saying that is because the images are represented using 1024 tokens, which is as big as the discrete latent codes they get from the VAE. And the total vocabulary size is 8192, which would mean that each discrete code is 8 bits. So I feel like then for the language model, you also have 1 bit per token.
So it's sort of a softmax. There could be only one in one position, like one and hot encoding, and then you can generate it the same way. One hot encoding.
I'm not 100% sure. So I'm wondering if it's a byte or a bit, a token.
Oh, maybe we can figure out later. It's just interesting how they represent their data.
Yeah, I agree. So for the images, it's pretty straightforward in terms of it's not straightforward, but they just sort of encode the images using a discrete VAE. But apparently, this byte pair encoding is often used now with Google and OpenAI to do language learning. So they also use this for GPT-3. Yeah. So that's most of what they tell about what they do. So or how they implement the model. I think in general it's just kind of the same as GPT-3. They just upscale a transformer model to be extremely big, and then they just look at what it can achieve. And that's also basically, so I'll go through it on their website. That's basically what they show as well. It's like most of what they do on their, so this is their blog post about what it can do. Basically, most of what it says here is just explaining like sort of what it can and what it can't do, basically. So for example, one of the things I thought was very cool is so we have Homer, for example, and what it can do is you can tell it to make a photo from each angle, and it will try and right. So you prompt it with a caption of a well-known figure and the top region of an image, and it will try and sort of recreate the 3D image of Homer. And here it says, we do this repeatedly, each time rotating the hat a few more degrees, and find that we're able to recover smooth animations of several well-known figures. So this 3D image is made by sort of creating this image prompt and just going over multiple angles, and it will generate each of those samples, and you can make a 3D model out of that.
So it's like just a bunch of different beards.
Yeah, that's what. Yeah, but they look pretty good. Like so this 3D model is made by rotating creating like multiple rotated versions of this image prompt, and then fusing that together. But yeah, in general, it's mostly just different beards, which maybe Homer just had like different beards on different days. I don't know. Like, but so it's pretty cool how consistent the generation is, because it means that to stitch them together in 3D, they need to be pretty consistent over a 3D sort of yeah. So if you rotate an image in 3D, so a 3D model, and give it 2D pictures, it'll be able to sort of grasp the 3D context of it, is basically what they're trying to say, because the completions are consistent over 3D sort of. So that's pretty cool. There are also things like you can give it a prompt like this, a capybara made of pixels sitting in a field, and it can just generate a 3D model instead of a sort of 2D image, which I thought was also pretty cool. Yeah, so here they say, able to modify the surface of each of the animals according to the chosen 3D style. So you can do claymation or voxels, and it will render the scene with plausible shading. So that's pretty cool. Yeah, they also have one, right? So I'll try and find that. But they also have one which says like X-ray, and you can see through. Let me see. Maybe further down. Yeah, no, I can't find that quickly. But for example, also it can combine unrelated concepts. So this is a snail made of a harp. or a snail made with the texture of a harp. And these images kind of look like they could have also been made by humans. In some way, they look like a good, like what you would think of if you read a snail made by a harp. This is kind of something you could come up with yourself. Like, it's pretty funny how, because obviously it wasn't trained on images of snails made of harps, because that, I don't think they exist that much.
So Harsh has a comment. Can you interpret that not on images, on the vocabulary?
Yeah, so the PBE is on, yeah, I just saw the comment. Yeah, so the PBE is not on the images, it's only on the vocabulary. The way it does the encoding for the images is using a discrete pre-trained VAE. So basically, you have the image caption and you have the image. The image is 256 by 256. And what they do is they encode the vocabulary using BPE, so by pair encoding, and they encode the image using a discrete VAE.
The image is represented using 1024 tokens with a vocab size of 8192.
Right.
So there is a sort of tokenization happening there too, relative to
That's a
encoding.
discrete. That's a discrete VAE.
They're not doing a further pre-processing step after the VAE? Is the question?
This is,
no? Okay.
So the discrete latent codes are the tokens.
Okay, that makes more sense.
Yeah, and then they sort of interpret the image and the vocabulary tokens as being sort of being in this sort of same data space, I guess. Although they try, of course, try to map from vocabulary to image, but I think they interpret them both as like bit maps or something.
Wait, how would you have a latent map that's constrained to 8? Never mind, I'll shut up.
So actually, okay, so what they do is that you have discrete VAEs, and you can trade, so they're, so discrete VAEs, they have a latent space which contains, for example, 8 bits for each latent dimension.
Okay, that makes sense then.
Right, and so they train it using a relaxed way, but then you quantize them sort of. So the training is done, you have like stuff like VQ VAEs, which do quantization in the latent space, so that
Gotcha.
you force your latent space to be discrete. And that's what they use.
Right, makes sense, sorry.
No, that's actually a good question. Because, it's an interesting field as well, but it's just, I don't know if we've looked into it much, but it's a big field in terms of, sometimes it will be, it's great to have discrete representations of images instead of continuous representations. And this is an example of this, because it's easier to represent it as tokens if you have discrete representation. Okay, so there's multiple. They do like a lot of tests on this model, which is, I feel like that's basically what the whole kind of premise of this is just training this huge model and then trying many different types of prompts and seeing what kind of output they get. Right, so what they're doing here is making a sketch on the bottom. So that's the image, that's the text prompt they give in. And you can see that the sketches are pretty good, although sometimes they are like very different from the way the cat is sitting in the image.
It all comes back to cats every time.
Yeah, right. They also have dogs, by the way. Someone who is into dogs, they also have the same thing for dogs. But yeah, it's really cool. Like of course, you know, you're waiting for like the full paper, but this is like, this is really cool stuff. I mean, GPT-3 was pretty cool already, but this is also like, it seemed like the combinations are very natural, I feel like. Yeah, so you can just finish geometric shapes and stuff. It can generate photos of certain streets. This one looks pretty good. Yeah, it's just, this is also pretty funny, like a photo of the food in China. I don't know. What do you guys think? I think this, yeah, so the way I kind of, I talked about this with Sergey as well, it's more of a discussion thing, because obviously this is like a, it's just like, what does this mean for?
I love the pattern examples. You see the one that completed the patterns, because
This one?
yeah, this one, because it seems like the normal IQ tests that we take. So I wonder what this model would perform on a regular IQ test. Like if it give it, the IQ test, they give 8 of these samples and want you to give the last one. So I wonder, like, what IQ does this give?
That's an interesting question.
It
kind of makes me.
Sorry, are you suggesting like text Turing test?
Yeah, but it's like very visual, and it's like the standard IQ. I just want to know what's the IQ of this model.
Yeah, this particular one, and I just Googled it because I forgot the name. It's called Raven's matrices, and I took it once, not too long ago, and it gets like successively harder and harder and harder to guess the pattern, to complete the pattern. So
Yeah.
those visual models, we could test them without like being able to speak to them.
Right.
Actually, he mentions the IQ test in the caption on the right. Right, it says rather than treating it says IQ test. So I guess that they did have that in mind.
Yeah.
Oh. But so
Yeah, it doesn't say what it scores though.
So I was wondering, what kind of applications does this have other than like maybe Photoshop 2025 or whatever? Like, I could see as a designer, it would be really nice to be able to use this, but like, what else could it do?
Yeah, that's a good question. It
kind of reminds me of like Word2Vec a little bit, where like, like the analogy completion with like king is to queen, is man is to woman, or something like that, where you like have vectors that represent these concepts. Like, is there any like any explanation of like how it's doing its reasoning in terms of the space that it does its reasoning in? I think that kind of is related to the previous question, because if this is like some form of general intelligence, then they're only testing it in a visual space. Then
right, so that's the whole point. It's just a transformer model. It's just one super big transformer model. I think that's kind of the whole point, is like, it's just like, I don't know if it has like a point in terms of like a practical application. I can see like startups, the same happened with GPT-3. They opened GPT-3 and all of a sudden there were like startups that were like, we can, generate the code for you if you start your, like there were all these like cool new startups. There probably is, like, especially in the film industry, you can see this being interesting. But I think in general, what they're trying to show is just like, if we go really big, we can have models that have really interesting behavior that seems close to
creativity. Right,
exactly. I think that's kind of the point here, is like, if you just scale up to 12 billion parameters, look at what it can do. And it's just a transformer. Like, there's no tricks involved. It's just like a really big model with a lot of self-attention layers.
Well, I was
go ahead.
I was impressed by what little I saw of GPT-3, because like in the context of like text summarization, because like it seemed like with LSTM or RNNs, you get like really crude text summaries. With LSTMs, you get slightly better, but still crude text summaries. With like GPT-2, you get pretty good ones, but with like GPT-3, it's like almost like you could probably pass the Turing test. And so these models are like getting closer and closer to being able to replicate functionality that we as humans have prided ourselves on being better machines at. And so if I don't know if this breaks into our domain, but I would say that this is about to break into all domains simultaneously. That's probably that was my takeaway. Maybe I'm a little too optimistic in terms of machine learning, but it seems to be like the progress is made by the ivory towers, and it breaks into everything faster and faster.
Sometimes it takes 1,000 years, though.
Yep. Maybe so. I doubt it.
I think this is really cool in that a lot of the VQA stuff is trying to establish reasoning between image and text, and being able to generate that backwards is generally viewed as a harder problem, or I would view it as a harder problem, even though it seems hard to judge as well, just like VQA is. And so in general, this is really cool that you can do something so simple and get something so good.
Right. Yeah. That was my takeaway as well. I mean, they just used 64 self-attention layers. That is something they did say in their blog post. I don't think they're doing like a lot of tricks necessarily. They're what they said in the GPT-3 paper is they try to make a network that is as task as agnostic as possible. So they don't try to do any CNN stuff or convolutional layers. They just try to make it as task agnostic as possible, but just make it really big and just see what it can come up with, sort of. And I feel like this is kind of the same way. And what they can come up with is very impressive, visually at least.
Yeah,
because that's of course the question.
It's really impressive in that the captions do really correspond with the images and have almost semantic meaning.
I have a startup idea, Eric, for you. It's a $1 billion unicorn, like day 2. Just start doing it and you'll get there.
You've got my attention.
Yeah, imagine, well, soon mass production, like soon we will be able to go beyond mass production and do on-demand production. You just call someone or log in on Amazon, like we have print on demand. We can produce merchandise and things like that on demand. But as soon as we have that, so we don't need the storage and stuff. As soon as we have that, because it will be automated, 3D printed, I don't know. So as soon as we have that, I want, as a customer, to be able to call or to log in and say, hey, I want a bread machine that can do this and this and that, and I want the blue buttons on the bottom that they match my kitchen and blah, 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 blah. And this will generate me the thing. And I was like, yeah, something like that. But how about whatever, the snail and a harp written, drawn on the side of it. And so it will generate, I will look at it and I will approve and I buy, and they will produce it immediately. Like
You say like I want a time machine, and then it'll.
I think I'm looking at William's window on my screen. I think 2 years, right? 3, not 2000.
Yeah, I mean, this is kind of this is the sort of what you're saying, but for fashion, I guess. Like you could just say a male mannequin dressed in orange and black flannel shirt, and it just.
Ooh, that's
there
for
you
a
have it.
type of industry.
I mean, yeah, this is like very cool in terms of like if you're a fashion, you can, because the thing is you can maybe like zero shot generalize it on like your design style. And you can just say like, okay, I want to have a dress, and it just generates like 100 types of dresses, and you're like, yeah, I kind of like that design, and you sort of finish it up. You like, like Vogue's next collection will just be they just sit back and they say, okay, what do we want to put in the collection? Okay, a dress. They just select one of the 100 dresses and they finish designing it. If you want jeans, they just.
Well, it's kind of going, because we're catering to the least common denominator, and because of that, the whole population sort of gets dumber. But instead of going this sort of populistic route, we can also think about on demand for creators. Like, I want a turbine for my home project or something like that, but a specific one. And I have to spend, like, I don't know, hours, nights and weekends in my AutoCAD or some CAD design for them to make it as I want. If I could just like describe it by words and people within my field would like understand me, then if this thing would understand me as another engineer would, that will be amazing. Like, it will save me so much time. I can put an offer and they will powder print, metal powder print, practically 3D print, but that technology existed for decades. What I want. And I will just build my rocket next SpaceX in my backyard or something like that. So, I mean, amazing opportunities potentially.
Yes, I'm going to play the devil's advocate here because I think Sergey's got the optimism side covered. I'm going to play the pessimistic side of this. So when I was a developer, like, we used to kind of like, the developers would kind of joke that the frameworks come out so fast these days that like, and they do more and more of what the developer's supposed to do, and the developers can't really keep up with them. That like the ultimate goal of the framework is to basically replace the developer. And at some point, this thing will be able to read all of GitHub and probably keep up with coding practices faster than developers. So at some point, I would think that this will probably replace industries, and that will cause economic problems that we haven't seen as a species, I would say.
Well, Steve Pinker's response is that all of our history shows that new technologies create many more jobs than they replace.
It's possible, but also exponential growth is hard to. We usually extrapolate linearly. If you replace industries slowly, then you can adjust. But if you replace industries so rapidly that by the time you retrain yourself, a new industry is born.
There is no exponential growth in nature. It's an abstraction. There is only an S curve.
Yeah. Well, there's an S curve, and then there's a breakthrough, and that S curve turns into something that looks exponential.
Well, of course, S curve looks exponential with our myopic vision of it at some point.
Yeah.
Question for VQA. If we were looking at this, VQA then fails because we don't have good language, because image and text look very well aligned in a number of these cases. So if we had as good representations and if they were as closely as related as this suggests, then do our language models or our ability to pose the question really have the issue?
What do you mean?
So if the images and if the text are as closely related as this suggests, that we can generate such good images from text like this that relatively closely map to our perception, then do we simply have either bad ways of doing VQA, or do we have bad ways of posing the question?
I'm wondering if it says they're close together, because a 12 billion parameter model with 64 layers, you can, the nonlinearity you can map is like, they can be very far apart, but because the model is so big, it can learn like that is,
Yeah, but it has some sort of meaning there that's fairly good, which is the interesting portion, right? And then if that meaning was actually translated for whatever question answering model, then that would be like, you would know that, for instance, is there a bed in the picture, and is it a white bed?
Yeah, so I think one thing that is interesting is that I think, so it maps the language tokens to the discrete VAE tokens, right? And then the pre-trained VAE maps it back to the real image. So the question is, how important is that? Because the 12 billion parameter mapping is between the image caption tokens and the discretized VAE tokens for the images, right?
Yep.
So the question is, how sort of far away are you from a pixel space using the discretized VAE already? Like, I feel like that could be, you know what I'm saying? Like
Well, yeah, the question is like, if I would assume that we had views discretized VAEs for BQA and that, and this is an assumption because I don't follow the field closely. But like,
Someone is asking a question about
ahead.
unseen data, right? But this is all looks to me like unseen data if we look at how it mixes. But I would rather Eloy, you answer his question in the chat there.
wait 1 sec, let me just pull it up to make sure I'm answering it correctly. 1 sec.
I think by unseen data, he means like if you don't have table in your original thing, in your original dictionary, and you say table, what happens? Is that what you're saying, Solomon?
No, but that would be like impossible. If I hear a word that I don't know, I don't like, well, unless it's in the context.
So, I don't know. The data sets they use are so big that I wonder if there is anything that is completely unseen in that sense. Like the amount of language data they use, I expect that they have every word probably in those data sets. They don't have every combination of words. Would you consider that unseen? For example, like
maybe Solomon can answer. It's his question.
right, yeah. No, I had the chat open so I can see. I can see. For example, like this stuff, like a snail made of harp. This is definitely not in the training set. Like there's no snail made of harp photo in the data set, and there's also probably no image caption saying a snail made of harp. So would you consider that unseen? Or this one, an illustration of a baby daikon radish in a tutu walking a dog. This is definitely not in the data set, but it can generate it like in a pretty natural way, it seems. Look,
Well,
probably the words.
It's seen radishes,
Right.
it's seen tutus and dogs and stuff. So in that sense,
Right.
use some kind of a random Jabberwocky style, what will it do?
Yeah,
Oh yeah,
exactly.
that's what I mean. It has seen radishes, dogs, and tutu, which is why it can construct this, I guess, right?
Right. So I think there's no true unseen data in that sense. I feel like most words, or at least like normal words, are in the data set and are also represented in the images. So obviously daikon, radish, and tutu and dog, they're all probably in the data set somewhere. There is an image with a dog, there's an image with a tutu, there's an image with a radish. But the beauty of it is that it sort of creates this latent space where these things can be merged together in a natural way.
A quick question because of the radish and the tutu. How did they prepare training data? Was it matched? I just missed that part. Text to images, were they matched or random or how?
Yeah, let me just check that real quick. Yeah, they just say like a data set of text to image pairs. I think they just generate them themselves. There's just like they do like a walk on the internet basically. I think they did the same thing for GPT-3. They just do like a big sort of.
So it's
I think they
and images or something like that. Images were with human captions or something like I just.
Yeah, I think so. So yeah, they don't make these things very open before they publish the paper, and even in the paper they kind of. I don't think because for GPT-3 they did some like some like scraping, and they don't say exactly how they scrape. They just tell you like, well, we got so much from Reddit, we got this much from whatever. And I don't know if they do like human annotated.
Well, because coming to our application, I don't know if Harsh is still there, but Eric, David Goodman, and others, I would like, or radiologist would like to be able to say, show me the images of a knee with this particular disorder and blah, blah, blah. If they see a new patient, they want to see historical, maybe how patient with these symptoms looked like. But maybe if this thing generated it realistically, they could compare or something like that. But
I
then
could see like a disease progression, like show me what this guy's brain is going to look like in 5 years, knowing that he has, this condition like Alzheimer's or whatever.
and with very, very little training data. Well,
Yeah.
like, I don't know where we can take the pairs, how many pairs there will be there for Alzheimer's.
Right.
Yeah.
So one thing I would say against this is that because it's trained using like maximum likelihood, it's very smooth. Sort of the images are like I think it would. It feels like it's just mostly focusing on the mean, sort of the mean pixel. Okay. For example, the walnut. Like these images are very smooth, but they don't contain like the details you would expect in a walnut, right? So it's not modeling the details you would need on like an X-ray image, I feel like.
So it's kind of blurred a little bit.
I see
Yeah,
all
that's
the details I need from a walnut.
This is
But
kind of
Yeah.
like
Okay,
this is
but
kind of like the
for-
problems I'm struggling with the folds of the brain going away with.
right. That's what I mean. Like if you look at this walnut, like you miss a lot of the information you would need for the brain folds.
well, maybe it's because it's 256 by 256.
Yeah.
Right.
Well, also
Yeah, but-
like smoothing, like they do a lot of smoothing in brains, like in neuroimaging anyways. So I don't know if that would be a huge issue, but yeah.
True. But this is like very smooth. Like if you
Oh,
look at this
right.
walnut, for example, this almost looks like a 3D render of a walnut more. I mean, I guess it
This
is,
reminds
but-
me. This reminds me of video games like 15, 20 years ago.
Well, that's what it is though, right? It is a 3D render.
Yeah, no, I agree. Yeah, but still, I mean, if you would generate a brain and it would look like this, it doesn't really tell
Oh.
you, like if it's this smooth, I feel like it's hard to determine if there's any, yeah.
I think it'd probably still provide some utility for people because you don't need like total precision. You just need like some kind of just good enough to be practical to get some kind of clinical application. But I don't know. That's pretty far off, probably. But yeah,
We just need quantum computers to make this so we can use them.
But to Kevin's questions, to what you're saying, Eric, like kind of additional bit, if I understood you correctly, Kevin, it would be cool to have reverse from image to text to help blind people to describe their surroundings, right? If that's possible. But this goes only one way, from text to image, right?
Yeah, if the reasoning is so good from text to image, then it stands that image to text could be good. Question marks. Why not?
Yeah, you would say that this is harder than the other way around, sort of.
but aren't they already doing that in other projects, like where they create a caption based on the image?
Yeah, I think that's a big field. I think this is one of the first times where it actually worked the other way around, because it's harder to generate a lot of pixels from text, which is way more like concise. Basically, it's a way more concise way of representing an image in terms of caption than the other way around, right? Like you go from like a huge pixel space to a smaller space like the image caption, and in this case you go from a very small space to a very big space, so you have a large like freedom in terms of choosing what pixel is what color, what like. So I think that's why it's hard, and that's why they use the discrete VAE stuff to make it easier, because you don't have to map to every pixel, but you can just map to a discrete sort of VAE latent space.
So one devil's advocate example, there was long ago, there was some work from Google maybe, or from someone before neural networks, where you could compress your images by finding a superposition of minimal number of differently colored polygons. So you just find those polygons and say triangles and their descriptions, and by overlaying them, you just create an image. And since Pedro Domingos is telling us that those are nothing but k-nearest neighbors kernel machines, so maybe what it's doing is just taking all of the images from this 175 billion cell memory and just carefully putting the weights and overlaying them on each other so we can see, like it does some kind of a Fourier out of those images, like basis decomposition.
Maybe. Yeah, I mean, yeah.
So do you think
I
they're
get
gonna
what you're
do you think they're gonna do movies next? Like make little animated GIFs?
Maybe. I would also
Movie
imagine
on
they would.
demand.
Yeah, exactly.
Yeah.
Yeah. Show me a movie about I don't know, the Night Stalker. I don't know. And
Right,
then it'll
exactly.
just create
I think
Yeah.
the first step would probably be to go to bigger images.
Mhm.
And then I think movies are definitely very soon to follow. I think they're probably working on that already.
They
because
definitely want to do that. That's for sure.
But I think one of the most problems that I have is with abstract concepts. Like if you tell this model to paint me draw me a painting that shows solitude, I don't think it will work. It's just with visual stuff that works, like not with abstract concept. So I think before jumping to videos, we have to, they have to solve this problem first.
Yeah, I feel like this is definitely an intermediate work where they also look at what it's learning, right? So that they can sort of go closer to the abstract reasoning problems. Because the geometric stuff that we just talked about with the IQ test, I think that's a step in the direction of abstract reasoning, but it's definitely not there yet. So I wonder if they're probably going to look at, how can we improve the abstract reasoning of these types of models so that we can sort of move. That's what I feel like they're doing anyways with GPT-3 as well. They're just training these huge models, and then afterwards they're just basically dissecting them and seeing like, okay, but what do they learn?
Yeah, about what they learn, I was just thinking to myself, it's interesting that like there's these massive advances, but have they gotten rid of all the adversarial problems of neural networks that have been observed in older versions of neural networks? Like what are the adversarial problems with GPT-3? Like what are their major reasoning flaws? That would be nice to know.
Well, it's very racist, for example. That's a big problem because it's trained on.
Is that because of the corpus, or is that because?
Yeah, corpus. But the problem is, every corpus is biased in some way.
Right.
So the question is, yeah. So, but the problem here was that if you would put in stuff like a Muslim walks into, and then it just said something like into a bar and it blows up, like that was the consistent way it would finish the sentence, which is not good at all. Like it's very, very bad.
It's terrible.
Yeah, there are actually a lot of people that say you can't publish this if that's still like a very real thing, because they're using it in like industrial applications now, which is a bit shady. It's like
I'm definitely the advocate of safe AI. I think that was OpenAI's mandate, is to like make sure that AI is not only in the hands of major corporations that maximize profit motive.
Well, actually, they sold it to Microsoft, or they sold like a main license to Microsoft. So,
well, there goes that idea.
Yeah, GPT-3's main license is to Microsoft now. Like they can, you can still license GPT-3, but like Microsoft can actually look at the model. Like you can only have like the input-output license, and Microsoft can actually see sort of like the model itself.
Does anyone have access to the beta, by the way? The GPT-3 beta here?
I don't.
Okay. So I'm looking in the forums, and people have tried it, and they're complaining that it cannot output simple stuff like 4 glasses on a table, even though it's a very well-defined concept and stuff like that. So
right. So definitely, it's not perfect or good yet.
Yeah.
So I agree. So this is definitely the first step, just the first step for GPT-3 and also for this.
But I think for a lot of people, it opens up this like, you know, this could very well be good in a few years, right?
Yeah.
Like, I think a lot of people hadn't expected that it would work this well. For example, with GPT-3, I think a lot of people would not have expected the way it could generate newspapers this already, like in 2020. Like, I think a lot of people were surprised by how natural it looks. Yes, there's a lot of problems still. I think it will probably take a long time before like it's ready for like safe use. But in a research context, it's like a pretty impressive step.
Well, I want to add another kind of optimism to it. Say steam engine, Greeks have already invented it back in the days, but we needed all of the little pieces of the industry to come together for actual industrial revolution to start. So here we can treat this either from a utilitarian like perspective, engineering perspective, how do we use this? Or we can treat this, what can it tell us about how the brain works? Or can we connect it to how the brain works? But in all honesty, I think we will need everything in order to like, for this to work, we will need knowledge from neuroscience and lots of development there. We will need, like this by itself, I don't think is gonna like solve all of the problems. But it's a piece that should be there and pieces of technology. And just that piece, 175 billion parameters, how many hardware engineers had, you know, died developing all this hardware that could run?
Jeez. Yeah.
Yeah, I think that's what I'm saying. Is like this is like a flavor of what's to come in a way. Like it's definitely not a whole meal yet. We can't do anything with it yet. It's not finished. It's just like it's in the work still. But it's like it shows people that if you have a lot of parameters, even now with like our sort of early bird neural networks, if you just scale it up to like 12 billion parameters, you still get results that are pretty cool.
So, okay, thank you very much, Eloy. Next time we will have a more engineering talk about Power SGD, how to train large models on remote machines or across machines. But this was interesting too. See you all next week.
Bye.
Thank you.